Okay. We're going to start out by me killing you all, or most of you. You're going to wonder why? Well, we're just going to make believe that we're in the 14th century in Northern Europe. This is the end of the Middle Ages. A lot of bad things were happening. In general, most people didn't make it out of childhood. Like most of you in here will just say, okay, you're all dead except for you. You're alive. Just want you to know. Are you happy about being alive? No. Okay. So I thought, okay, you're dead too. How about you? Are you happy to be alive? Okay, because you're going to breathe, right? And that's going to be a good thing. Well, maybe. Maybe not, you don't think so. But you want to pass your genes on. And over here, hello, you're alive. Okay. You're going to have 15 children. No. Oh, yeah. Absolutely. This is good, except that, of course, 13 of those are going to die by the time they reach 10 years old. But so be it. You still end up with 2. Okay? You're going to live 2, and the rest of you are dead. Okay. Now, it turns out in childhood, when there wasn't any modern medicine, now there was medicine there, remember, it was pretty much like witchcraft. So instead of going to a doctor like we do, who has actually got training, you go to someone who was a witch doctor, and it's usually you got sick because someone put a spell on you or something. Okay? So that's why you didn't necessarily work, but maybe you felt better afterwards. Who knows? There was also bloodletting, to kind of clean out the blood. That was a nice way to actually do doctoring back then. So in this group, again, most of you didn't make it out of childhood. Mostly died of digestive disorders, like some parasites in your gut, or respiratory diseases. Now remember, little kids, they don't have a very good immune system. It gets trained as they get older. And so, plus, they didn't know anything about sanitation. And then, of course, there were lots of other infectious diseases. And that's where we're going to come over here to this group. All of you died because of the plague. In 14th century Europe, about 1346 to 51, or maybe longer, the bubonic plague came into Europe and wiped out about maybe over half the population. Whole villages just got wiped out. Kind of like, you guys know what the Ebola virus is? Anybody in here who's afraid of it? Oh, good. Okay. It turns out Ebola is not as, what should I say? It's not as contagious as some other diseases, like measles. Turns out measles is one of the most contagious diseases out there. If you're in a room with someone with measles and they're shedding virus, there's a 90% chance you're going to get infected. So I'm going to go back to that in a little bit about vaccines and all that. But in this case, bubonic plague, you guys all got wiped out. Now, that's pretty, if you look at how many people actually survived until adulthood, at that period of time, perhaps 800 out of 1,000 people or more didn't make it. They never made it to adulthood, where they could actually breathe. It was also unusual for parents to actually live long enough after that to actually see their kids grow up, get married, all that kind of stuff. They usually died before that happened. It was a pretty brutal existence. All kinds of things could kill you, not just diseases. famines. The crops might fail. And then some people would survive because they had a phenotype that allowed them. A phenotype is our anatomy, physiology, behavior, everything that makes an organism an organism. There's differences among organisms. All of you are somewhat different. Anybody in here have an identical twin? Oh, that's good. So are you identical in terms of personality? Maybe not, but still pretty much. So it turns out you're as related to your twin as she's related to you, which is one. You share the same DNA as your twin. The rest of you, if you have, let's say, your fraternal twin, or your sisters or brothers, you're related by half. And we'll get into why that's so. So where was I going with that? I kind of forget. Okay, so anyway, what was I saying before that?
You all died.
Oh, you all died, right? Okay, I knew that. Something else. Okay, right. So now, of course, nowadays that doesn't happen. Has anybody in here been so sick with an infectious disease that they almost died or they had to go to the hospital? No? Okay. I once got a strep throat, and oh, by the way, the plague is easy to cure nowadays. Antibiotics do it. Of course, they didn't have antibiotics back then. Some people still die of the plague. It's usually carried in rodent populations. And if a doctor doesn't recognize that they have the plague, and they don't actually get treatment soon enough, then they might not catch it until it's too late. But in general, people don't die of the plague anymore. But they do die of, like, Ebola. They don't, let's see, there's a lot of things that we don't die of, obviously. But I had strep throat once, and I got really, really, really sick. I did end up in the hospital, but it took me about a month to actually recover. Now, it's because it was a bacterial infection that I survived, because they put me on antibiotics that worked. If not, I'd probably, well, I'm a ghost. I'd be standing here, and I wouldn't be standing here. There'd be someone else in this class going through, talking to you about that kind of stuff. So things have really, really changed. Now, there are still some parts of the world where it's not that way. You go to some parts of Africa and the developed world, and you find that there's a very large number of individuals who never make it out of childhood. The average lifespan, oh yeah, back in the 14th century, what do you think the average lifespan was? What do you think? A little higher. But you're right, the median was probably like 12. 35, okay. So, it's not that people then didn't live long. There were always a few people who did. The thing is, most of the people didn't make it out of childhood, right? And so, the average lifespan was like 30 or 35, but there was a big variance. There was a lot of people that died young, and then there was other people that made it to 30 and they bred, and other people that made it to 55, that would be an elder. Okay? They might have even have been someone who lived till 80. But the proportion of individuals who made it to that age, at that time, or let's say in equatorial Africa, would be small compared to what it is in a modern society. So, the average lifespan now is about 80 years old, plus or minus, depending on whether you're male or female. Now, that's all the result of modern medicine. Now, the reason I'm bringing this up, I have an ulterior motive here. The U.S. government has been cutting lots of different programs. Now, after World War II is when U.S. science actually blossomed. And not just modern medicine, but material sciences, chemistry, physics, all sorts of different things that made the internet possible, made all sorts of different things possible. And it worked by this way. There was government funding that people at universities would apply for in grants. And then there were, and that was, a lot of that was just basic science. That means, well, we'll get to why we do science in a second here. But it was learning how things actually work. And then there was companies, pharmaceutical companies, things like that, that would actually then take the basic science and turn it into something useful. Well, the proportion of our federal budget that now goes to supporting research and development has taken a huge hit. Now you might say, well, we're all living pretty good. But some of you in here, at one time or another, are going to get really sick. And without new discoveries, you're going to die. That's just the way it's going to be. So when you hear people saying, oh, that's not all that important, I just want you to remember that everything that you do in your modern life is pretty much the result of scientific discovery. That if it wasn't there, the average lifespan would be 30 to 35 years old. Now, some of you are, most of you are young. Anybody older than that? Than 30? No, you're all young. Huh. But hopefully you're going to get to 30, 35. But before, there was this kind of, now, science really didn't really, I would say modern science didn't really start, well, modern medical science, let's say the 1700s, with vaccination and Edward Jenner, who found out about vaccinating people against smallpox. But since then, there's been huge strides made, and so that's pretty much why we're all here, and we didn't die in childhood. Okay. Oh yeah, one other thing. No, let's see. Let me just get on with it. Okay. I brought up the bus for a reason. I want you to think about this. I don't want any answers yet. We'll get to it later. Do anybody know in here what natural selection is? Anybody know what you do? What is it?
Survival of the fittest.
Okay. Survival of the fittest. Anything else? Yeah?
Pretty much getting rid of the bad gene from the gene pool and replacing them with the good genes to better suit the organism.
Okay, good. So, now, selection we're going to find out operates on a bunch of different levels. It can operate on survival. It can operate on sexual reproduction, like why do you find some people attractive compared to others? It can operate on like fecundity, how many offspring you actually leave. But in terms of survival, we'll just kind of look at it this way. So, if I step into the road and I get smacked by a bus and flattened, I become flat and fall on the roadway, is that natural selection? Yes. Anybody else? Okay, I want you guys to think about that. We're going to get to it. But it's a kind of an interesting question. And we'll see why later. Okay. Oh, let's see. Yeah. Measles. Has anybody in here not been vaccinated? Everybody has. Maybe someone hasn't that perhaps they're too afraid to admit it. There's a measles outbreak going on. Now, 15 years ago, there were no measles cases in the United States at all. None. Absolute zero. It's because there was a vaccine for measles, among other diseases, that was developed in the 50s and 60s. And kids got vaccinated, and they didn't get measles. And so that if everybody was vaccinated, or at least 95% of them, the chances of a contagious disease like measles would not spread. Someone might get it who wasn't vaccinated, but everyone around them would be vaccinated. It's called herd immunity. And then nowadays, all of a sudden there's these new outbreaks of measles. And anybody, why is that happening?
Because parents aren't vaccinating their kids.
In fact, it's interesting, there's this whole anti-vaccine movement. Anybody know why?
They think it's linked to autism.
Autism, right. So, when does autism show up? What do you think? Young, late?
Very young.
Young, okay. When do you get vaccinated?
As a baby, as a child.
Okay. Now, some people, there's this whole movement, it's actually among very well-educated people. People who should know better. And so you have these clusters of people. Let's see. Some people in Northern California, some people in Connecticut, all these places where there's kind of well-educated, wealthier people who think that anything that's not natural, they shouldn't use. And it's actually opened up the chance that we actually have measles outbreaks nowadays. Now, in science, we try to find out kind of what's going on. And we do it a certain way. We see something, phenomenon, let's say the measles outbreak. We ask, why is it happening now and not in the past? And we find out that some people aren't getting vaccinated. And we ask, why aren't they getting vaccinated? And one answer might be that they just haven't thought about it. Another, that they think it's actually linked to autism. And so let's say you have this explanation that you think vaccines are linked to autism. Now, that makes a prediction. So, an explanation is essentially a hypothesis. That's all it is. Hypotheses are a dime a dozen. It doesn't matter if they're good hypotheses or not. as long as they can be tested. So a hypothesis that links autism with vaccines, there's a correlation there for some reason. Correlation does not mean cause and effect. It means that things are associated with each other in the same place at the same time, things like that. That's all it is. But let's say we have this hypothesis that vaccines actually cause autism. The prediction, let's say you had two groups of people. In one group, you gave them a vaccine, and in the other group, you didn't give them a vaccine. You gave them placebo. And if, in fact, it was linked to autism, which group would have a higher incidence of autism? The one that got the vaccine. Versus the other one would have less. Now, if there was no, yes?
Isn't autism related to like their genes also?
Yeah.
So wouldn't you have to like track their genes to be
So
sure?
that's another hypothesis. So we're talking one hypothesis, but absolutely.
But wouldn't it be based on multiple things?
It could be, very well. But in this case, we're wondering about whether there's a correlation between autism and vaccines causing autism. But there's, in fact, there are genetic changes that are also associated with autism. That's another hypothesis. Okay? There's a lot more evidence for that than for the other one. So, the group that didn't get the vaccine, if in fact there was no cause and effect, you would see the same number of cases of autism in each group. Versus in the vaccine group, you'd see a much higher incidence of autism, right? Well, it turns out that the vaccine-autism connection has been debunked. That there's absolutely no difference between people who get vaccine and don't get vaccine and the incidence of autism. But some people thought, well, young kids get vaccines, there's got to be a reason for why they get autism, and it's the vaccines. That's a correlation. Perhaps we could say that let's see, now I'll have to think of something different about cause and effect. We'll get to that in a second. But anyway, that's kind of what's going on now. Well-educated people, now there's oftentimes same sort of things going on with all kinds of people. Beliefs, a belief is something that may or may not be true, but we don't know. So, for example, we might say, here's my keys. Why did my keys fall to the floor? Gravity. Okay. Anybody else have another explanation for that?
You dropped them.
Huh?
You dropped them.
Well, I know, but what's causing them to fall to the floor? Gravity. Okay. Any other explanation? It can be a crazy explanation. Anybody else? Witchcraft.
God.
Okay. Huh?
God.
God. Okay. What if I told you that there were little men with metal magnetic heads under the earth? That's actually the reason that my keys fall to the ground. That's a hypothesis, right? That's an explanation. Now, if it was magnetism, these metal head guys, that was actually causing things to fall to the ground, what prediction could you make? Now, what does magnetism generally work on? On metal, right? Did I hear that? Okay. Well, these are metals, so they fall to the ground. Do you have any metal in you? In you?
No.
No.
Yeah, yes.
Oh, you do?
My tongue ring.
You?
My tongue ring.
Oh, shoot. Okay, forget about you. Anybody else? Do you have any metal in you? None. How come he's not floating off into space? Now, if it was the metal heads, that's a prediction you would make. Right? That only metal things fell to the ground because of the metal heads, the magnetic heads, and the rest of everything else would float. So, we made a prediction. You can actually test that prediction, can't you? We could actually test it. In fact, we've already tested it just through observation alone. We said, oh, all you guys are not floating off into space. Amazing. It must not be metal heads. We haven't established what it is, but we can certainly say it's not metal heads anymore. We've what's called falsified. So, I guess I'm going to ask, I want some definitions of what science is. Anybody? I know there's some people who've got a definition of science. Huh? Yeah.
Study how things work.
Okay. Actually, here. Oh. Come on. Okay. Oops, I walked, that doesn't work, but anyway. Anything else? Yeah?
Explanations for natural phenomena.
Okay. Oh. Come on, there we go. Okay. Anything else?
How something is created.
Okay. How something is created. It's not working. Okay. Anything else? Okay. We have those other explanations. You could say it's a systematic enterprise that builds and organizes knowledge in the form of testable explanations. Testable is the operative word here. And predictions about the universe, natural phenomena. Science is actually it's only a method of thinking. We have other methods of thinking. Who in here is a philosopher? A philosophy major? Anybody? Who in here is a journalism major? How about history? What do you guys do?
Theater.
What?
Theater.
Theater. Okay, good.
Psychology.
Hmm?
Psychology.
Psychology.
Business.
Hmm?
Business.
Business. Okay. You guys should get together. No, you and him. And open up a business together about theater. Okay? You can connect later on. Okay. There are many ways of knowing things. Religion is another way of knowing something. So, in the scientific method does something kind of strange. It's counterintuitive. What that means is, instead of being, oh, it seems like it should, it's obviously that way, it's not. When you walk through your lives, you think you know what the world around you is all about, perhaps. And do you normally just have a belief about how things are, and perhaps people look for confirmation that their beliefs are true? Science is a little different in that when we come up with an explanation, we actually try to blow it up. Now that seems strange. Why would you do that? Well, it turns out that if you're trying to confirm everything you see, all you're going to look for is things that confirm it. But what happens if you really want to figure out if something is in fact true or not? And that trueness may be something that you think it's true, or maybe you think it's not true, but you want to find out if it's actually true. And so in general, I guess what science does is, instead of looking for confirmations for an explanation, you actually look for a way to show that it's not true. Hence, the metalheads, or the vaccine and autism, right? If I really believed in metalheads, I'd look to confirm it, right? And I'd say, oh, see, it's metalheads. But if I'm a scientist, I would say, okay, what are the predictions? Well, one of the predictions, of course, was that if that's metal, if it's magnetic metalheads that are causing things to stay put, then everything else should be floating off into space. Well, we just falsified that prediction that's central to the hypothesis of metalheads. Now, we haven't established why, in fact, we stay put. That's another explanation. But we can actually show that, in fact, metalheads is not an explanation. Same thing with autism, right? Make certain predictions people have tested those predictions, which is if in fact vaccines cause autism, then individuals who get vaccines should have a higher incidence of autism than individuals who don't. Right? And the falsification has turned out to be true. You're able to falsify that vaccines do not cause autism. The same incidence of autism occurs in people who got vaccines versus those who didn't. Okay. So that's kind of the scientific method. Instead of looking to confirm something, we actually look at a way to show that it's not true.
Silent water under the rocks and stone. There is water underground. as it ever was, same 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 as it ever was. Time isn't holding us, time isn't after us, time isn't
Well, we kind of answered this, why do we do science? To figure out stuff, right? So really, there's kind of an ultimate reason. I guess you could say, just to figure out what the hell's going on. Not what you might hope is going on, or what might be going on, but what's actually going on, just trying to figure out what's going on. Of course, there might be a practical reason for figuring out what's going on. You find out something that's going on, the cause of it, and you realize, oh, well, there's a practical application of that way of thinking. So, let's say, who drives here from far away? Okay, where?
From Carson, like 35, 40 miles.
Okay, anybody else?
Oak Park.
Huh?
Oak Park.
Oak Park?
60 hours.
Thousand,
Thousand Oaks?
LA,
LA?
Lancaster.
Okay, Lancaster? Okay. Which way do you come to work? Let's say Lancaster.
So which way?
Which way? How do you come?
I get on the freeway.
Okay. What happens if there's a lot of traffic? Do you ever get off the freeway?
No.
Okay. Anybody else get off the freeway and do something else? Yeah?
Sometimes they work through the street.
Surface streets. Okay. So, did anybody go a certain way and they kept going that way? That's just the way they learned and that they stayed that way, right? That's a possibility. All of these things are different ways of kind of knowing things. The question is, you often want to know, well, what's the fastest way to get to school? Now, maybe you like driving in traffic, and so forget about that for you. You're out of here. But everybody else wants to get here as quickly as possible. And, of course, perhaps the fastest way is the freeway. But what is it dependent on about the fastest way? Is it, what's one reason for why it might be fast one way and not another?
Distance?
Huh?
The distance?
The distance, that's good. Anything else?
Traffic lights?
Traffic, or traffic lights, but also traffic. So, back to you. So sometimes you get off and you go on surface streets. The freeway's blocked, right? So that's why you do it. And you're hoping to cut a little bit of time off. When there's no traffic, what do? Freeway. Right. Okay. So, this is an explanation. You say, oh, I go this route because it's faster. Now, that's just one data point. That's one person. But to actually figure out why, which is faster, what you probably would do if you were a scientist, you take 10 cars that all go the freeway with traffic and without traffic. And then you go another 10 cars that, if there's traffic, they go a different route, the surface streets. Now 10 is so that you're getting a sample, and it's not just one anecdotal individual, it's actually, you've got some data here. And you find out that depending on how much traffic is, certain ways to get there are faster or slower. That's a practical reason. Now, you might say, well, that's not really science. Well, the same sort of, science is a way to think about things, or it's a method. So, I think we'll take a little break, for, let's say, 10 minutes, and then we'll come back here. Okay? Good.
Hi.
Hi.
So I'm actually in upper division biology. I'm taking genetics, cell bio, and principles of microbiology.
So why are you in here?
I needed to fill up enough units to get financial aid, and this was the only class I could get into in my schedule.
Okay. Well, it's not helping you, obviously. Yeah. So are you a biology major?
Yeah.
Yeah.
Microbiology.
Oh, okay. So you've already had 106 and
107.
genetics and all that.
Yeah.
Okay.
But I do have to take it because otherwise they'll take away my financial.
Right.
Um,
You can't get into anything else that helps you?
I looked for Russian. I thought of taking geology and astronomy. They all got filled up by the time I could do.
Okay.
And then everything else I could find conflicted with my other schedule.
Yeah. Well then, you're no good. Okay. So what do you want?
But I have a PLF for genetics that starts at 1.
Oh, sure. Go ahead.
So I'll probably stay here as long as I can to do the assignments.
Yeah.
So
Right. Exactly. So that's fine. Absolutely.
just wanted to let you know.
No, that's great. Thanks.
I know they emailed you, but I'm late. I just wanted to touch base with you.
Okay. You're late?
No, I'm just gonna add late.
Oh, you're gonna add late. Okay. So, I think there's some open spaces, so you should be able to add
Okay.
automatically.
But I emailed you, I can't add all my numbers, I feel like I have to wait. I'm doing like a season.
Oh, that's right.
So I just wanted to
Okay.
make sure you see that I'm doing good stuff.
Okay.
Fine.
Okay. I'll make sure that. Let's see what I'm gonna do. Okay. I'll talk to the admissions and records. 1 second. Let me write
I
this.
know that I can be manually added to Moodle. For my other class, I got manually added, and I have full access to like turn in work and everything.
Oh, really?
Yeah.
Okay. How did they do that? They don't know? Okay.
He just put in. I know all he asked for was my full name. It didn't even require my ID.
Okay, good.
So I was just touching base with you. I'm gonna use the restroom, but I'll be back.
Okay. 1 sec. Let me just write this down. Okay, yeah.
I'm the one that emailed you.
What?
About joining your class.
Oh, this class? Yeah.
Then I also need a permission so I can add it myself.
Why not?
I go through same college.
You go to what?
Go through same college.
Oh, you do? Well, no, you should still be able to.
I'm in the same boat. I'm going, or at least I'm going through Open University.
Yeah.
And through Open University, you need a
Really? Okay.
permission number.
Oh, I didn't know that. Okay. Let me find out what's going on with that. What's your name?
Sydney Missouri. SYD. NEY.
Okay.
NASSIRI.
I think you're. Hold on a second. Hold on. God, I remember seeing your name. Okay, I'll look into it. Okay. And what's your name?
Nick Bruno, or Nicholas Bruno.
Okay. Oh, your name too. Okay, I'll find out what's going on.
Okay, thank you.
Okay, hopefully, we're not giving out any permission numbers, but hopefully we can, I can kind of close the waiting list,
Okay.
and then you'll get in,
Okay.
okay?
Thank you.
I just want to tell you I'm thinking of going absent for next class because I will have driving lessons. I just want to make sure if I'm going to miss out on anything.
Okay, so all this is being taped,
Yeah.
and you'll be able to go to that
Yeah.
and check it out anytime, so you won't really miss anything.
And you told us that the top hat should be done in class. So
Yeah, so when you get the next time you come, or email me and you can come to my office and do those.
Okay.
Okay?
Okay. Thank
That's
you.
great. I swear. Okay. Okay. Good. So this is kind of where we left off. There is, everybody know where Caltech is or what Caltech is? Anybody doesn't? Caltech is like one of the top research universities in the country for physics and stuff like that. A lot of different things. It's kind of like MIT back east. And they have a lot of Nobel laureates there. And one of them, Richard Feynman, he's dead now, but he's an incredible guy. But anyway, this is his definition of science. And so let's first start out. So, if we look for a new law, or let's say a new explanation, where do we come up with the explanations? Well, we can guess. Simple as that. Now that seems kind of crazy, doesn't it? Oh, just guess. As long as we can test that hypothesis by the predictions it makes, it's a valid hypothesis, and then we can find out whether it's wrong. Not necessarily whether it's right, but whether it's wrong. And then by computing the consequences, we mean we make predictions. Now, with a physicist like Feynman, the consequences are, it's quantified, And it's usually some quantifiable number to, let's say 10 digits. So let's say 1.0015677, something like that. That's a prediction. Then we compare those computation results to nature. In other words, nature is empirical evidence, the stuff we can actually measure. And we want to say whether that prediction that we made is the same as what we actually find. So, like we did with caffeine or with the vaccine, we made a hypothesis that vaccines cause autism. We made a prediction about which group would have the highest incidence of autism. And then we convert correctly and see if it works. If it disagrees with the experiment, in this case the autism thing, it does, it means it's wrong. In that simple statement, that's the key to science. You want to be able to prove things wrong. What that is called is falsifiable. If a hypothesis is not falsifiable, in other words, if you cannot prove it wrong, then it's not a scientific hypothesis. You have to be able to test it and to show that in fact it's wrong. Either with observation or just with logic. It doesn't make any difference how beautiful the guess is, the hypothesis. It doesn't make any difference how smart you or I or anybody else is. Who made the guess, or what the name is. If it disagrees with the experiment, it's wrong. That's all there is to it. Now you say, okay, we know something's wrong, how do we know something's right? Well, let's say we do an experiment with, let's see, okay. We say, if you get strep throat, and we want to know if a certain antibiotic works for it. So, we have a group, people who have strep throat who get either the antibiotic we're looking for, or a placebo, or perhaps a different antibiotic. We want to know which one works the best. Let's say 3 different antibiotics, A, B, and C. We show that the patients that got antibiotics A and C haven't gotten any better. Patients, I said, in other words, multiple patients, not one patient. Has to be multiple. But we see that people who got antibiotic B got better. So we disproved A and C. We didn't prove B. It could have been something else perhaps that we didn't control for, but it works. And then someone else replicates the experiment over and over and over. You do trials with a whole bunch of people, and you find out, in fact, that antibiotic B does work. It doesn't mean necessarily that it's true. It could still be some small chance that it's not true, it's something else. But as evidence accumulates that you cannot falsify that B doesn't work, you get to what's called conditional acceptance. You say, it appears that this is, in fact, antibiotic B actually works. Now, if something down the line comes along, some new information, and you find out something new, you find out, in fact, that, let's say, antibiotic B only works on people of a certain age. Then you have to modify your hypothesis because you found something new. Or let's say you find out that it's all a correlation between taking antibiotic B, and something else in terms of the patients, and you find out it's only a correlation, but there's actually something else that's actually causing it. Then you have to toss out your hypothesis and say it's wrong. In fact, it's not antibiotic B, but it's something else that's actually causing people to get better. Okay. Oops. So this is the method this is kind of a schematic of the method that we do. Generally, we make an observation. Not necessarily, though. Sometimes we know enough that we come up with our own hypotheses about something that happens, but we'll just say we start with an observation. The car won't start. Naturally, we want to know, why doesn't the car start? Right? We come up with an idea. There could be a whole bunch of different things that it won't start. We could say, perhaps it's the battery. Perhaps there's no gas. Perhaps rodents made a bunch of nests throughout the engine, and it won't start because of that. They're all hypotheses. By the way, the last one actually happened to me. Okay? Goddamn rats. So, the car won't start because the battery's dead. Okay? This is a hypothesis, right? Now, it makes a prediction. It has to be a prediction that you can test. If the hypothesis is correct, then the car will start if we replace the battery. It won't start if we put gas in it instead. Of course, the way to test that is to do an experiment or an observation. In this case, we're just going to do, now, it can be an experiment like I talked to you about individuals who get a treatment, individuals who don't. They don't know, each individual doesn't know which one they got, and the doctors don't know which one they got. That's an experiment. Or it could just be like with the dropping the keys. The prediction was with the metal heads that, well, it should only work on metallic objects and not on everything else. And of course, we could easily falsify that just by looking around. That's an observation. Okay. So, then we do the experiment. Now, if in fact we replace the battery and the battery starts, the dead battery hypothesis is supported. Now, it doesn't necessarily mean it's true, but it's likely to be true. And if you did this over and over again, you would find out, in fact, that let's say it's true. But, right here, what happens if it's not true? It's not that you've replaced the battery, you just spent $110, nothing happens. Okay. Then you have to come up with a new hypothesis. That's also falsifiable. In my case, it was rats and they'd shoot through the cables. So, at first I thought it was just a dead battery, but then I found out it wasn't. It was rats. Of course, I fixed that. I fixed it. I got the cable fixed, and then of course I went out and started killing rats as quickly as possible. I know I'm a meanie. Okay. So, a question is, we kind of talked about this with Feynman. Where does a hypothesis come from? An observation. Just a guess. This is a hypothesis. The universe revolves around the Earth. Is it or isn't it? Why not? What? Oh, no, I know, that's true. But is this a hypothesis? Can you disprove this? Yeah. So this is a hypothesis. It turns out it's a wrong hypothesis, but it's still a hypothesis. Let's say you go out, you look outside in the morning, pouring down rain, and you decide it's best to wear a miniskirt. Is that a hypothesis?
No.
Why not?
It's not a question.
Well, you can disprove it though, can't you? You can say, oh, this is a hypothesis, I'm going to go out in the rain and wear a miniskirt, and I'll be fine, and it turns out you're not fine. Right? You just disproved it. How about which route to take to school? I believe this route versus this route. You test it. You say, oh, in fact, I'm wrong. You can't just test it once, but you have to do replicates of each. And then you find out, oh, well, sometimes it's right and sometimes it's wrong. These are all hypotheses. A hypothesis does not have to be right. It's nice when it's right, but it doesn't have to. Okay, so the question is, should we look for evidence to confirm it? Huh? Yes. Okay. Why? Okay. So let's say about the way to work or way to school. You go and you take the freeway and you get here in a certain amount of time. And every time you take the freeway, you get here in a certain amount of time. Except for sometimes, when there's lots of traffic. So, if you look to confirm it, and that's all you see, you confirmed it, but you haven't really found out, in fact, whether that's the fastest way to work depending on the traffic. Should you look for evidence to refute it? Well, you can certainly find out that, oh, if I go this way on the freeway and there's no traffic, I get here in a certain amount of time. But if I take the freeway and there's lots of traffic, it's faster to go some other route. So we've kind of partially refuted it. We said, okay, you might say the freeway is always the fastest. We've just disproved that. We said, oh, that's not necessarily the case. That leads us to questions about why the freeway is not always the fastest way to go, which then generate more explanations because of the traffic. The traffic is correlated with the time of day, right? This is falsifiability. This means that you can disprove something. you can, now, if you keep getting an answer where you actually disprove things, and you haven't been able to disprove it, that means you're getting evidence that in fact supports that hypothesis. You're not getting it because you're confirming it, you're getting it because you're failing to falsify it. And then over a long enough period of time, that information, it looks like there's support for that hypothesis. As I mentioned, you might find out something later that causes you to either reject the hypothesis, there's actually something else, or to modify it. But you get conditional support. Conditional means depending on any new information that you can actually change it. This is the only way you can actually know if something is true, if it's proved. But we really can't prove things absolutely, can we? If there's always a chance that new information in the future comes along and you can reject that hypothesis, then it means that, okay, that means there's uncertainty. Now, at a certain point you get to a level, let's say we have antibiotic A, B, and C again. Antibiotic B always works. There's support for it. And that's what's prescribed to people who have a certain disease, bacterial disease. But we find out eventually, are we done? Holy moly. Really? Okay, hold on a second. We're going to end this right now. But we find out that, someone has this disease, we know it. We did we sampled the blood and found out that it grew this bacteria. So we know he's infected with the same thing, but he doesn't get better. Why do you think that might have happened? Huh?
The virus evolved.
The bacteria evolved, evolved, yeah. It was an antiviral as a virus, same sort of thing. So in other words, there's been resistance that has evolved in certain strains of that bacteria. And we say, well, it used to work, but it doesn't anymore. In that case, we modify it. We say, it works on these strains, but not on this. Okay? That's what it's all about. Anything else that doesn't allow you to test that is not a scientific hypothesis. It's an explanation that might be true or might not be true. But you have to be able to blow something up. If it's still standing, after you've thrown nuclear weapons at it and death rays and everything, you've tried everything that you could possibly think of and other people have, then there's conditional support, very strong. You've actually shrunk the uncertainty about whether it's true or not. But until you do that, all bets are off the table. Okay, thanks.
Professor,
Yeah.
I have a question. For the Sim Bio, once we register, are all the questions up for the semester? And we can just do that?
No, I'll set it with a date. Which ones are due at certain times.
Okay.
So I'll set that up.
Okay.
Hi, how are you?
Good, how are you? What
Good.
are you teaching? Same thing?
Yeah, I'm 100, yeah.
Alrighty.
Yeah. What's up?
I'm just back. I'm done. So I'm back because remember in the beginning of the semester, there was you said if there's an issue about the field not taking that one unit, it shows up on the map that you'll have to just sign it off. So it comes up as an X for that one unit.
Okay, so you're missing a unit.
Yeah.
Okay, you're gonna have to go to the biology advising office.
They can sign it off.
Right.
Okay, and if
Exactly.
anything, should I just tell them that I checked with you and,
Yeah, I mean, the thing is, if you're only missing one unit,
yeah.
they'll probably sign
Yeah,
off
because
on
it
it.
was for the field study and I already took the field for vert.
Right.
The lab, so it was that.
Oh,
one.
okay, yeah, that's a,
It was
I've had
my-
other people doing
Me,
this.
Christina, and Anite had the same issue.
Exactly,
Yeah.
right.
Okay.
Yeah, no, that was a problem.
Yeah.
It seemed, it's a system
Yeah,
generally.
yeah,
So
exactly.
if you add up all your units for whatever your major
should be-
is,
it's done.
and you're fine, then it's just the system, but go there
Go over
and
there.
what they'll do is, they'll do some little funny things and make it
And then
right.
make it work. Okay,
Yeah.
thank you.
Sure, okay.
Have a good semester.
Okay, you too.
So I have to make 2 accounts, one for Symbio and the other for 12 hat.
Top hat,
Top hat.
yeah.
Do we have to do top hat in class? Or
Yes,
can
it's always gonna be in class.
we, like do it at home?
No. That means you have to come to class. Unless, of course, you come to school and you have an accident and you can't make it to class or something like that. Then you can come to my office and do it, but otherwise, no, you have to be in class to do it.
Alright, so top hat is for class and Symbio is for, and,
Whenever you want.
can I use my phone for top hat?
Yeah, you can. So once you, if you follow the instructions for Top Hat and set up an account, then you'll be able to use your it's an iPhone or a smartphone, right?
Alright.
Yeah.
I can make the account at home, right, for top
Yes.
hat? But I can't like do anything with it.
You can't actually take the quiz, no, at home. You can actually set it up and then in here, we'll go over and you'll be able to find out if it works or not, and we'll make sure by, let's say, the 3rd week that everybody's on the same page, that they can actually answer things, and then we'll do it in class.
Alright.
Okay?
I just want to ask another question. Like, given that I won't be here, I cannot be here on next Friday at